All right, you should have out lecture notes 21, expected value. And I say here our context is, as before, we have a discrete random variable x, and we have its probability distribution. So we have a chart that has the values of the random variable, and the next column it has the various probabilities. Okay, and I just have a little bit here that you might want to just pause me and read, and then I'll go over it very quickly before we do the example. So pause me and read that. And okay, I'm just talking about, imagine doing the experiment that results in the different values of the random variable over and over and over and over again, and keeping track of all the different values that come up and how often they come up. We could compute the relative frequency of each value, which is like the empirical probability of each value. So suppose we generated a big data set like that. Do you remember that we could compute the mean of a discrete random variable by taking, the mean of a discrete set of discrete data, by taking each value times its relative frequency and adding them all up. Well, what I say here is, let's think of the probability distribution chart for a discrete random variable as sort of an idealized version of the relative frequencies chart. It's a relative frequency like for the whole population of all possible data the random variable could generate. The result is, by the law of large numbers, all those relative frequencies should converge to the real probability. So the probability chart sort of gives us an idealized relative frequency chart. With that in mind, we could use that to compute what we would call the mean of the random variable. So what we're doing is we're computing the mean of an RVX. And that's also called E of x, which is the expected value of x. Okay, and it's going to be a little bit clearer if we just immediately go into an example. So I say here, let x be the number facing up when we toss one fair die. We've done that before. Compute the expected value of x, and there I say that's the standard notation for the expected value, E of x. So for example, so we have an experiment is toss one die, x equal the number facing up, right? There's our random variable. We want E of x. What we're going to do is we're going to take the probability distribution chart for the random variable x, capital X. Here are the different possible values. We know to be 1, 2, 3, 4, 5, and 6. And we know the probability of each one is 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. What I'm going to do to compute the expected value of x is I'm actually going to tack on another column, and what that will be is it will be each value times its corresponding probability. So I'm going to take 1 times 1/6, so that's 1/6. I'm going to take 2 times 1/6, so that's 2/6, which of course I could write as 1/3, but I'm going to leave it in terms of sixth. I'll take 3 times 1/6, so let me divide these here. 3 times 1/6, and that'll be 3/6. I'll take 4 times 1/6, and that'll be 4/6. I'll take 5 times 1/6, which will be 5/6, and I'll take 6 times 1/6, which gives me 6/6 or 1, right? Okay. And what I want to do is add these up. I've run out of room down here. In fact, can you even see? Yeah, you can see the bottom here, but I can't go below. So add up this last column, and you get 21/6, which is 7/2 or 3.5. 3.5. All right, what I've really done, isn't it the case, is that I've taken a weighted average of the values of x. Each possible value is multiplied by its weight or its probability. And here it's kind of boring because all the probabilities are exactly the same. But here is my expected value. So the expected value of x is 3.5. All right? 3 and a half. And what I say here is, how should you think about the expected value of x? Think like this. Certainly, I make a note there at the bottom that this so-called expected value, it's almost kind of humorous to call it the expected value because you never expect to toss a die and get 3.5, right? You're going to get 1, 2, 3, 4, 5, or 6. This value that we have here isn't something you'd ever expect to get in a single toss, but the way to think about expected value of x is to think it's the, what I like to call the long run average or long run mean of x. Meaning, if you perform the experiment over and over and over, toss the die over and over and over, and record all the values you get and record their frequencies, you can take each value times the relative frequency, and what will happen is you'll have a number that's close to 3.5. If you keep tossing and tossing and tossing, the number will get closer and closer to 3.5 when you compute the mean using those relative frequencies. So in the long run, it's the average of the values of x, right? And it turns out to be 3.5. Next example is, let's suppose we toss 2 dice. So let the experiment toss 2 dice and let x equal the sum of the numbers facing up. And I say find the expected value of x. So you should go back and take the table that you have, the probability distribution table for the case of tossing 2 dice, the values for x and the probabilities, put in a third column, do all that multiplication and add them down and see what you come up with. So pause me and see if you can get that. Okay, I'm not going to do the whole work. I'm just going to say here's x. And here again, x is my random variable, right? So I like to keep it capitalized. And little x means all the different possible values for the random variable. And over here I have p of x, or again, I could write it as p of capital X equal that little x, where this little x is the same as this little x over here. Okay, and the various values, that's what I've actually done over here, right? And the various values are 2, 3, and it's going to go up to 12, right? And for 2, it was 1 over 36. For 3, it was 3 over 36. And all the way back down here is 1 over 36. So I'm going to do a third column. And I do hope that you've gone through and done all this. This is going to, when I multiply across, I'm going to get 2 over 36. Here I'm going to get 9 over 36, right? That all the way down. This will be 12 over 36. If you add them all up, you get what? I think you get 252 over 36, which turns out to be 7. All right, so the expected value of x here is 7. Okay, which maybe shouldn't shock you too much, since tossing 1 die, the long run average is 3.5. Tossing 2 dice, the long run average or the sum is double that, 7. Shouldn't be too shocking. All right, let me do the next example very quickly. So I say a modified game of craps. You can read it here. Just a very, very simplified game of craps where you toss 2 dice and you win depending on what values come up. And it's much more complicated than what I have here, but I just simplified it to give you an easy example. So you are tossing 2 dice, but first you pay $1 to play. You toss 2 dice. If you get a sum of 7 or 11, then you win $4. Otherwise, you lose your $1. What are your expected winnings? So what that means is, what would be your long run average win every time you played if you were to play the game over and over and over? So the way to think about it is like this. The experiment is toss 2 die. Experiment is toss 2 dice, And now here, what I want our random variable to be, our random variable, I'm going to call it W, because I don't care necessarily about the exact sum I get. I just care whether or not I win money, right? So I can think of this as an outcome of either I win or I lose. So I'm going to call my random variable W, and what I win each time. And I put win in quotes. W stands for win, but of course, if I end up losing, I'll think of it as winning a negative value, right? And with that in mind, let me see if I can write the probability distribution chart for my random variable W. So I have W here, and I have P of W here. This is the right way to think of this problem. It seems very different from what we thought of before, but it's actually quite simple. My random outcome here is, what matters is, did I win or did I lose? If I win, I get a certain amount. If I lose, I get a certain amount. So let's imagine if I lose. So this would not be part of the chart, but this is kind of just a memory device to help you realize what we're doing. If we lose, what would it mean that we won? Well, it says that we pay $1, and then we play, and then we don't get anything if we lose. But we paid that $1. So what we have won is a negative $1, right? We have lost $1. So our winnings are -1. If we win, what does it say? We're given $4, but we've paid in $1. So what we've actually won is 3. Sound good? What is the probability in each case? Well, let's see, I have plenty of room. So to win, we need a 7 or 11. So check your chart for tossing 2 dice. The probability, if you look at the area of those 2 bars, the area above 7 was 6 over 36, and the area above 11 was 2 over 36. So I get 8 over 36, which if I pull the 4 out and cancel, it's 2/9. So that is the probability for winning. So ending up with $3 has probability 2/9. What does it mean to lose? It means getting anything else. So to get anything else, that would mean I got a 1, 2, 3, 4, 5, 6, or 8, 9, 10, or 12, right? I can add all those probabilities up, but of course that's the hard way of doing it. Let me just use the fact that that would be the complement of getting 7 or 11, which means it should be, the probability should be 1 minus the 2/9, correct? So I'm running out of room. Do I have it right here? Okay, so lose, the probability is 1 minus 2/9, which is 7/9. So I have 7/9 right there, okay? Expected value, I've kind of run out of room here. I'm going to change color just to give me, in case just to have the contrast so that you can still see what I'm doing. So I'm going to take W times P of W, just like I did in these other 2 examples. When I take a -1 times 7/9, I get -7/9. When I take 3 times 2/9, I get 6/9. Then I'm going to add them up, right? So I'm going to have to come right here and say the expected value of W. That's what I want. When it says what are my expected winnings, my random variable is W, what I win, so I want E of W. E of W is -7/9 plus 6/9, which is -1/9. So on average, I win -1/9 of $1. So in other words, I lose, it's about 11 cents. And let me say again, that's on average. I lose about 11 cents. I will not lose 11 cents in any one time I play it, but if I play it over and over and over and over, on average, I'm losing 11 cents every time. Let's do the final example. And I have to rub out a little bit. Okay, so you read it and actually see if you can set it up and work it. So pause me while I'm racing here and see what you can do. I guess if you pause me, I won't actually be erasing for you, will I? But see if you can read it and get there. I can say we got, what do we have? We have a $20 raffle ticket for a car that costs $25,000. You buy one of them and they sell 3,000 of them. So what's your expected winnings? Okay, so once again, so in this example, I'm not going to write it up. I'm going to say it's the raffle ticket. Okay, so W equals your winnings. So the possible values for W are either I pay my $20 and I don't win, so I lost 20, I have a negative 20 winnings, or I pay my $20 and I win the $25,000 car, assuming it actually is of that value. Won't I get a winnings then of $24,980, right? Because I lost the 20, I don't get that back. So there's my winnings. What are the probabilities? Well, the probability of winning, I bought one ticket out of 3,000. So my sample space of all tickets is 3,000. I bought one, so it's 1 over 3,000. Therefore, the complementary event that I lost has probability 2,999 over 3,000. Okay? I want my expected winnings. So let me compute W times P of W. And when I do that, here I get what? I get negative 59980 over 3,000. And here, of course, I multiply across, I get 24980 over 3,000. So expected value of W equals this plus this, right? It's negative 59980 plus 24980 over 3,000. And that works out to be negative 11 2/3. So lose about $11.67. Again, I'm never going to lose that amount if I do this, but suppose every day I got up and there was a new raffle and I bought a raffle ticket and it was the exact same circumstances. If I did it over and over and over for, a billion times, I would expect on average to lose that much. How do I lose that much on average? The answer is I lose this much over and over and over and over and over again, and once in a very infrequent time, I will win that much. And then I'll lose and I'll lose and I'll lose, and eventually I'll win that much again. If I keep going forever, my average winnings will be that I will lose $11.67. And of course, that's the point of a raffle, right? You don't want the people who are buying the tickets to have a positive expected value. That means the people who are selling them would have a negative expected value. This is the way the house works when you go to Vegas, right? At Vegas, the gambler plays something, whether it's a slot machine or blackjack or whatever, they play a few times, and either they win or lose, right? But the expected value is going to be negative. That means the house's expected value is positive. If the house is playing this game, let's just think of slot machines. If it's playing those slot machines over and over and over again, because so many people come in and play them, that on average, it wins a little each time. Most of the time, it's winning because it gives out nothing back, but once in a while, it gives money back, right? But it doesn't care about that because on average, it's winning a certain amount each time. That's where expected value comes in. It tells you your long run average. In this case, your long run average, if you did this over and over and over, is you'd be losing $11.67. Over here, this game, you'd be losing, what was it? Worked out to be, I think, about 11 cents, right, on average. All right, we'll stop there.